Hello everyone, welcome back to a new section and a new video from chapter 4. Now, remember that you have studied work in the previous years, and work was done when an object was moving in the same direction as the direction of the force applied. Let's say you have this object and you are applying a force in the right direction of the object, and the object is also moving in the same direction. We were saying that this is work done, but if the object was moving up and the direction was to the right, then work is not done on this object. We can relate this example to heat. Imagine you are trying to pull out a nail out of a wood. If you touch this nail when it's out, you're going to feel that it's hot. Why does this happen? First, when you are trying to take out this nail, you are doing mechanical work on the nail. You are trying to push out, you are trying to take out the nail. This nail, because it's moving, is going to have friction against the wood. This friction is going to cause the particles of the nail to vibrate faster and therefore increase the internal energy of the nail. And if the internal energy of the nail increases, it's going to heat up the nail. And basically you have more kinetic energy, and if kinetic energy increases, internal energy is going to increase too. Now, some of this heat energy is going to be transferred to the wood and to the surrounding area too. Heat can also do work. For instance, you have a flask, or if you have a bottle, and you have water. Okay, if you pour water into this bottle, into this flask, and you tie up a balloon on top of it, you'll see that the balloon is going to expand and push, and the steam from the water is going to push the balloon outward. This is basically heat doing work on the balloon. Work can also involve pressure and volume change. For instance, expanding or compressing a gas in a cylinder. We're going to talk about this one in a minute. But before that, we have two things: thermodynamic systems, okay, and environment. A thermodynamic system can be anything. For example, you have a fridge, and a fridge is a system because it removes heat from the substances and takes it outside. And we can study heat, work, and internal energy in this fridge. So this is basically a system. Environment is basically anything that can affect the system's behavior, okay? For instance, if you open the door of a refrigerator, you're basically affecting the system's behavior. We have three systems. Open system, for instance, while you are boiling water in a kettle, in open systems, there's going to be energy transfer and also matter transfer too, okay? And you also have closed systems. In closed systems, there is only one exchange, which is the exchange of energy. For instance, pressure cooker, okay? When you're trying, let's say, to cook meat and you put it inside a pressure cooker, you only are adding heat. Matter is going to be what is not going to be exchanged. It's sealed, the pot is sealed, and the steam from the water is going to be retained in the pressure cooker unless you open the lid of the pressure cooker, which is something you might not want to do. Isolated system. Isolated system is what? You have all seen thermos. Thermos is a really, really good example of isolated systems. There is no exchange of matter and there is no exchange of energy. So if you put hot water, for instance, in a thermos, you can see after 6 hours or 7 hours, the water is still hot. There is no exchange of matter or exchange of energy. Now, we have the equation for work. This is mechanical work, careful. Force multiplied by the distance. Okay, this is mechanical work. What if we want to find the we want to relate this to heat and pressure and change in volume. We have this, okay? This is when the volume changes or the pressure changes. So we have this question. It says, prove that work is equal to pressure times change in the volume of an object. Prove that work is equal to pressure times change in the volume. First of all, remember the equation for work. It is equal to force times distance. Now, if you remember, pressure was equal to what? Think about it. What equation do you have for force? You have force divided by area. Now, if I want to find force is going to be pressure multiplied by area. Put this instead of the F here, this one. Work is going to be pressure multiplied by area. And this is going to be what? This is going to be, we have A, okay? A is what? Okay, A and D, okay? A multiplied by D. This is what? Remember, volume was equal to length times width times height. And we were saying something else. We were saying A, area, this is basically area, multiplied by H. This H can be written as D too. H can be written as D. So volume is equal to area times distance. Okay, it's the same thing. Okay, they have the same meaning. Now, we have change in the volume of a substance. So we're going to say what? We're going to say delta V. Okay, so this is going to be work, pressure. Instead of this A multiplied by distance, I can write change in the volume. So delta V. This is what? This is the proof for this one. Prove that pressure work is equal to pressure times volume. Now, the unit for work is what? Is Newton per meter. It is what? Newton per meter, and it is the same unit as energy. Two very important notes that you're going to be needing is when the gas expands and it pushes the against its surrounding. For example, you have a piston and you are trying to what? You are trying to, or the gas is pushing the piston outward. Here, delta V is going to be positive, okay? And here we're going to say what? We're going to say that work is done by the system. This is really important. Here, if the gas expands and pushes against the surrounding, so gas here is doing what? You have a system, you have a cylinder, and you have gas inside of it. If this gas pushes, okay, expands the out to the surrounding, then this is going to be what? Work done by the system. And delta V is going to be positive. Careful. If the system compresses the gas, leading to a decrease in its volume, it's going to be negative. Here, work is done on the system, not by the system. Okay? The piston is compressing the gas, so basically the piston is doing work on the gas. Delta V is going to be negative. We have sample problem for D. An engine cylinder has a cross-sectional area of 0.01 meter squared. So we have our givens. It is really, really important to know how to identify the givens first. If you don't know, if it doesn't say area, then you should know that you have the meter squared. And meter squared is what is the unit for area. Area is equal to what? It is equal to 0.01 meter squared. How much work can be done by a gas in the cylinder? So it says what? How much work can be done by a gas in the cylinder if the gas exerts a constant pressure of 7.5 times 10 to the power of 5 Pascal. So pressure is equal to what? Pressure is equal to 7.5 times 10 to the power of 5 Pascal. Even if it doesn't say pressure, you should know, you have studied this in the previous chapters, that Pascal is a unit of pressure. On the piston, and moves the pistons a distance of 0.04 meter. Now what is this? Okay, this is meter, so it's distance. Okay, even if it doesn't say so, sorry, distance is equal to what? It is equal to 0.04 meter. What do we need? It says how much work. So work is equal to what? Remember, work is equal to pressure times what? Time is delta V. Do I have delta V? No, I don't. But remember, we had something else. We were saying delta V is equal to area times distance. Now everything is solved. Work is equal to 7.5 times 10 to the power of 5 times area is equal to what? 0.01 times distance is equal to what? Distance is equal to 0.04. Now what is the final result? The final result is going to be 3 times 10 to the power of 3 times 10 to the power of 2 Newton per meter, or joule. It's the same unit for work. This is it for today. I'll see you in practice 4D. If you have any questions, please comment below. I will gladly answer your questions. See you in the next video.